Welcome to our quantum deep dive.
Great to be here.
Today we're embarking on an incredible journey, really, into the world of quantum communication. And we're guided by the visionary, often called his father, Jian-Wei Pan.
That's right.
Our mission in this deep dive is to truly unpack how Pan took these almost fantastical ideas from quantum physics.
Ideas that still baffle people today.
Exactly, and transform them into a technological revolution. He basically laid the groundwork for things like unhackable encryption and maybe even a global quantum internet.
And for this exploration, we're drawing heavily from a really insightful essay by Jorgo Schneepad. We've tried to distill the most important nuggets from that source to give you a clear picture of Pan's work.
Absolutely. Because, this isn't just abstract science. Why does quantum communication matter to you, the listener? Well, it's all about its huge promise for secure data transfer.
Especially now, right, with digital vulnerability seemingly everywhere.
For sure. Imagine information so secure it's physically impossible to intercept without setting off alarms. That's the kind of future Pan is building.
Okay, so let's unpack this.
Yeah, let's dive in.
To really get what Jian-Wei Pan achieved, you kind of have to go back and grapple with the basics of quantum mechanics, which are, let's be honest, pretty weird.
Definitely counterintuitive.
Think back to the early 20th century. You had pioneers like Max Planck introducing this radical idea of energy coming in discrete packets, quantums.
Right, not continuous.
Then Einstein builds on that, explains the photoelectric effect, and gives us the idea of light itself being these little packets, or quanta.
Which was mind-bending at the time.
And then you get Schrödinger and Heisenberg developing the mathematical tools, the wave equation, matrix mechanics, the stuff that actually lets you calculate things in this new quantum world.
And absolutely central to quantum communication, and maybe the weirdest part, is quantum entanglement.
Ah, yes, Einstein's famous phrase. Spooky action at a distance. That's the one. It's where two or more particles get linked. Intrinsically linked.
So linked that measuring one instantly affects the other no matter how far apart they are. Miles. Light years.
Doesn't matter. The connection is instant. It really messes with our everyday ideas of cause and effect, How can something here instantly affect something way over there?
It sounds impossible. How did they even prove it was real?
Well, that's where John Bell came in. His work on the Bell inequalities gave physicists a way to actually test this experimentally.
And the test?
They proved it. The experiments confirmed that entanglement works exactly like quantum mechanics predicts, spooky as it sounds. It wasn't just some mathematical quirk. It was real.
Okay, so if this spooky action is real, how do you actually harness it? What does quantum communication mean in, practical terms?
Good question. Essentially, it's about using these weird quantum principles to send information. The main technologies are things like quantum cryptography.
For secure messages.
Exactly. It relies on entanglement and another principle called the no-cloning theorem. Basically, you can't perfectly copy an unknown quantum state.
So if someone tries to eavesdrop,
they inevitably change the state. It's like leaving fingerprints all over it. The act of observing disturbs it, and that elutes the intended recipients instantly.
Okay, got it. And the other one you mentioned? Teleportation.
Quantum teleportation, yeah. And it's not like Star Trek beaming people around. It's about replicating the state of a quantum bit, a qubit, somewhere else without physically moving the original particle.
Transferring the information, not the particle itself.
Precisely.
That's a completely different way of thinking at security compared to what we use now.
Oh, absolutely. It's a massive shift. What's really revolutionary here is moving from mathematical security to physical security.
Meaning?
Well, think about current encryption. It relies on complex math problems that are hard to solve. But, theoretically, with enough computing power, maybe a future quantum computer, they could be cracked.
Right.
But quantum communication offers security guaranteed by the laws of physics themselves. It's not just a harder lock. It's a lock that basically screams if anyone even tries to pick it.
That immediate detection is the key thing.
It fundamentally changes the game in cryptography.
Okay, so with these incredibly strange, almost sci-fi principles laid out, how does one person start turning this into actual technology? This is where Jian-Wei Pan comes in, right?
Exactly. And his story is pretty remarkable, too.
Tell us a bit about his background. He wasn't exactly born into a high-tech world, was he?
No, not at all. He was born in 1970 in Dongyang, which was then a pretty small rural town in China. Came from, quite modest beginnings.
But he had this curiosity.
An exceptional curiosity, apparently.
What?
Especially for physics. And crucially, this was during the time China was opening up in the 1980s, creating new opportunities.
And he grabbed those opportunities. He got into a top university.
Yes, the University of Science and Technology of China, USTC, in '87, a really prestigious place. And that's where he first seriously encountered these weird quantum ideas, superposition, entanglement.
And his professors saw something special.
They did. Not just theoretical smarts, but also a knack for experiments.
Yeah. Which
is a pretty powerful combination in this field.
Then came Vienna. That seems like a huge turning point.
Absolutely pivotal. He got a scholarship for his PhD studies in Vienna, working under Anton Zeilinger.
A big name in quantum physics.
One of the biggest. Zeilinger was a pioneer in entanglement and quantum communication. Working with him was crucial for Pan. It shaped his experimental approach, his deep understanding of quantum mechanics, both the practical side and the deeper philosophical questions.
What was he working on specifically in Vienna?
His PhD project focused on testing entanglement over greater distances. Still quite theoretical then, but a necessary step towards making it practical.
And he started getting results pretty quickly, making a name for himself.
Oh yeah, he didn't waste any time. Some of his early work involved experiments testing Bell's inequalities, showing entangled photons synchronizing instantly, even when separated.
Using new techniques.
Yeah, he developed more efficient ways to create entangled photons, better detectors, pushing the boundaries of precision and distance. His results got published in top journals like Nature, Physical Review letters. That really put him on the map.
It sounds like that early work really set the stage for everything else.
It absolutely did. It laid the crucial groundwork.
Okay, so let's dig into those bigger achievements then. He really focused on making entanglement usable, right? Not just observing it.
Exactly, mastering it for practical use. He worked on generating and manipulating entangled photons, finding ways to keep them entangled, maintaining those fragile states reliably, efficiently, and over significant distances.
What were the immediate implications of that kind of work?
Well, connecting it to the bigger picture, these experiments were vital. They proved that quantum networks weren't just a lab curiosity. They could actually work.
They showed you could have secure communication where any eavesdropping gets spotted immediately.
Precisely. Because messing with the quantum state leaves a trace. And beyond just communication, his super rigorous experiments provided really solid proof for quantum mechanics itself, especially by confirming those violations of Bell's inequalities. Foundational stuff.
Which leads us to that big milestone in 2012, the 100-kilometer quantum teleportation.
Yeah, that was huge. A direct demonstration of transferring a qubit's quantum state without physically moving the particle.
How on earth did they do that? It sounds like pure sci-fi.
It does, doesn't it? The setup involved entangled photons created over a fiber optic link, and then they used a clever technique called a Bell measurement.
Okay.
That measurement essentially lets you extract the quantum information from one photon and transfer its state to the distant entangled partner photon without moving the original.
Wow. Teleporting the state. Okay, so if we can do that, what does it really unlock? Does this open the door to that quantum internet idea?
It certainly points in that direction. When you can teleport a quantum state over real distances, the possibilities just explode.
Like what?
Well, you could potentially link quantum computers across cities or even continents, creating distributed quantum computing networks.
Right. Pooling their power.
Exactly. It also makes quantum cryptography even more robust. And it pushes forward our fundamental understanding of entanglement itself. It really makes you ask, if we can teleport a state, what are the ultimate limits here?
It's mind-boggling. And building on that success, Pan then spearheaded probably his most famous project, the Mencius satellite, launched in 2016.
Mencius, yeah. Named after an ancient Chinese philosopher, a truly monumental project.
And the concept was pretty brilliant, using space to overcome limitations on the ground.
Totally ingenious. Mencius was packed with high-precision lasers and detectors designed to beam entangled photons from space down to Earth station to bypass the atmosphere, essentially. Fiber optic cables on the ground lose signal over long distances, and the atmosphere itself can interfere. Beaming from space minimizes those losses dramatically. It allows for much, much longer distance quantum communication than was possible before.
So what did Mencius actually achieve? What were the results?
The results were, frankly, revolutionary. They instantly established China as a world leader in this field.
Give us the highlights.
Okay, first, they managed the first successful quantum encrypted message transmission over, get this, 1,200 kilometers between ground stations in China and Europe.
Wow. 1,200 kilometers.
Yeah. Mischius also demonstrated entanglement itself, surviving over these previously unimaginable distances. And, incredibly, they achieved the first teleportation of a quantum bit from a ground station up to the satellite in orbit.
From Earth to space. Okay, so putting it all together, what's the big takeaway from Mischius?
It proved that a global quantum communication network isn't just theoretical anymore. It's technically feasible.
By going through space, you bypass the ground-level problems.
Exactly. It opened up the possibility of a truly global, potentially unhackable communication infrastructure. It moved quantum mechanics firmly out of the lab and into the realm of practical, world-changing applications.
It's clear Pan is an incredible scientist, but he seems to be more than that, a real builder, a visionary. He kept collaborating internationally too, right?
Oh, absolutely. He continued working closely with people like Anton Zeilinger, his old mentor. He's really acted as a bridge, connecting research groups in China and elsewhere on these big, ambitious projects.
And what about his impact within China, building up their capabilities?
That's been hugely significant. You really can't overstate his role there. After returning to China, he founded and still leads the Institute for Quantum Information and Quantum Communication at USTC.
The university he attended.
Right. And that institute is now a global powerhouse in quantum research. It covers everything from fundamental science to developing scalable tech for crypto and teleportation, and crucially, education.
Training the next generation.
Exactly. Pan has put a lot of effort into fostering young scientists, scholarships, conferences, exchange programs. Building that pipeline of talent is vital for the future.
And he seems very focused on connecting the science to industry, getting it out of the lab.
Yeah, he recognized the economic and societal potential early on. He's been directly involved in projects building actual secure quantum networks.
Like the Beijing-Shanghai link.
That's a prime example, yeah. A world first, building secure networks for government and businesses. He's also pushed for collaborations with tech companies, explored using quantum security in finance. He's clearly driven by making a real-world impact.
So looking ahead now, what's Pan's grand vision? Where does he see all this going?
He sees quantum communication as the foundation for truly secure global networks. Unhackable security based on physics, not just math.
The quantum internet.
That's the ambition. A network that could offer absolute security for international communication, link up quantum computers and sensors across the globe, maybe even create disaster-proof communication systems. Mischius showed it's technically possible.
And you mentioned quantum computers earlier. There's a synergy there.
Oh, a massive synergy. They're like two sides of the same quantum coin. Quantum computers give you the processing power.
And quantum communication gives you the secure network to connect them.
Exactly. And that combination is where things get really interesting. Think cloud-based quantum computing, where users anywhere could securely access quantum resources. Or distributed quantum systems tackling huge problems in logistics, energy, medicine, problems way beyond today's classical computers.
Okay, it sounds amazing, but it can't be easy. What are the big roadblocks still? The practical challenges?
Oh, there are definitely significant hurdles. On the technical side, scalability is a big one.
Sending signals over vast distances.
Right. You still lose signal, even with satellites. We need things called quantum repeaters to boost the signal without destroying the quantum state, and while they're being developed, they're not quite there yet for wide deployment. Stability is another major issue. These quantum systems are incredibly delicate, sensitive to temperature, vibrations, any little disturbance. Integrating them into our existing messy infrastructure is tough.
And I imagine it's expensive.
Extremely expensive, yes. Especially the satellites and the high-precision components. Bringing the costs down through innovation is crucial for making it economically viable.
So technical hurdles, but are there also broader sort of societal or ethical challenges to think about with this powerful tech?
Absolutely. While the promise is secure data, you have to ask, secure for whom? There's a risk of monopolies, states or giant corporations controlling this ultra-secure network, which could definitely worsen power imbalance.
And could it be misused?
Like any powerful technology, yes. Could criminal organizations or rogue states use quantum secure networks? It's a possibility that needs consideration. And then there's the question of access and equality.
The digital divide, but potentially much wider.
Exactly. If only wealthy nations or groups can afford this, it could create an even bigger gap. So this really raises that important question. How do we make sure these amazing advances actually benefit everyone responsibly?
Has Pan addressed these concerns?
Yes, he has often stressed the need for scientists and policymakers to work together on this, to anticipate the challenges and guide the development responsibly.
Okay, so let's just recap Pan's journey. It's truly incredible. From that foundational research proving entanglement was real and usable,
to those mind-bending teleportation experiments over 100 kilometers.
And then the Messias satellite, literally reaching for the stars to build a global network. He really has taken quantum mechanics from theory to tangible, potentially world-changing technology.
No doubt. And looking ahead, he'll clearly remain a central figure. We'll likely see more breakthroughs from his team, making systems more robust, more scalable.
And he'll keep guiding the field strategically.
For sure. In the next decades, we might see those quantum repeaters finally become practical, leading to a real quantum internet. We'll see quantum computing and communication merge even more deeply. New materials may be the first truly commercial quantum networks.
So a final thought for you, our listener. As you think about all this, consider that Pan's work isn't just about faster internet or more secure emails.
It goes deeper.
It's fundamentally changing how we understand information itself and potentially our ability to control and share it securely on a global scale. It's a profound shift.
A really profound shift.
And remember, this deep dive drew significantly from that excellent essay by Jorgo Schneepat. If you want to explore more about quantum science and technology, you can find more information at schneepat.de.
Definitely worth checking out for more detail.
Thank you so much for joining us on this quantum deep dive.
Thanks for listening.
Goodbye.